Hello everyone, welcome to another lecture for General Physics 2. This one deals with inductors and capacitors in AC circuits. So one piece of this we've seen before. We've talked about capacitors before, but what's an inductor, and then what happens when you put an inductor and a capacitor into a circuit where the current doesn't flow in one direction but alternates back and forth. So let's take that first question, what is an inductor, on, if I can get the slide to advance. There we go. And think about this in the context of Faraday's law and Lenz's law, which we've just studied, and in perhaps one of the simplest circuits we could think about. So here I have a battery. The numbers on this image don't really matter, connected to a resistor, and there is a switch that can be closed. So when that switch is closed, we now have a simple circuit that consists of one power supply, one resistor. You could use Ohm's law to calculate how much current is flowing through there. But think about this from an electromagnetic perspective. I have a conducting loop. Previously, there was no magnetic field in the center of this conducting loop. But now when I send a current around this loop, it creates a magnetic field in the center of the loop, producing a magnetic flux where there previously was none. This actually causes the circuit to induce what is known as a back EMF, an EMF that's pushing against the direction of the current that is being established in this circuit in order to create a magnetic field which opposes the change of the magnetic flux in the center of the loop. Now, truth be told, in a single loop circuit, the size of this effect is so tiny and happens so quickly that you would never actually notice this, but in general, this is the principle of induction. So the magnetic flux is proportional to the amount of current you send. You send more current, you get more of a flux that's established and more of a reaction to that. And like we've done in many modeling labs so far, is whenever we say one thing is proportional to another thing, you can always make them equal by introducing a constant of proportionality. In this case, this constant of proportionality actually has a specific name and symbol. It's called inductance, and it's symbolized with a capital L. And in this example, it's known as self-inductance, sort of this induced change that opposes the effect in the circuit. So if we think about this circuit from the framework of Faraday's law, the induced EMF is equal to the negative of the change in flux with respect to time. I've taken N out because there's just one loop around here. And so if the flux is this self-inductance times the current, we could exchange the flux for L times I. And because L, the self-inductance, doesn't change, that can be factored out. So we could rewrite Faraday's law as saying the induced EMF is equal to the negative of the inductance times the change in current over time. Inductance gets measured in units of henries. I'm not sure exactly who that's named after, but it is abbreviated with a capital H. And if you are counting units and converting units from one to another, 1 Henry is 1 volt second per ampere, among other ways that you could write it in equivalent units. So while a circuit loop has some tiny amount of self-inductance, it is more common to see actual inductors put into the circuit. So if you did the lab in this section, you've seen a couple of coils that were used in the induction part of this lab. An inductor is any sort of coil of wire that can be inserted into our circuit. And we're going to talk about what the inductance of a coil would be using the things that we've talked about previously. So if we start with our definition of magnetic flux, flux, recall, is the product of magnetic field and area, but it's the magnetic field times the area times the cosine of the angle between the magnetic field direction and the direction of a vector that is pointing normal to the plane of the coil, or sometimes we just call that the area vector. Well, we have the magnetic field of a solenoid from a previous discussion. So if I'm talking about a long coil, that's the geometry of a solenoid. So I'm going to replace the magnetic field in this expression with how we calculate the magnetic field of a solenoid. Mu zero, the permeability constant, times the number of turns times the current divided by the length of that solenoid. So the flux looks like this, and algebraically I can rearrange however I want to here. I'm going to pull the current I to the end of this expression, because doing so allows me to compare with what we had on the previous slide. So if we have Faraday's law that the induced EMF is minus n times the change in flux with respect to time, that flux is all of this stuff that we have here. I just found the laser pointer feature on Google Slides. So that's going to go in here, and what of those things is changing? Well, if it's a situation where only the current is changing and the number of turns is the same and the area is the same and the length is the same, all the rest of those constants can get factored out. So I have minus mu zero times n squared times A over L times the change in current with respect to time. Hey, that whole form looks pretty similar to what we had on the previous page, in that we said that the induced EMF was minus the inductance times the change in current over the change in time. So if you compare the pieces that are similar here, it allows us to actually write a mathematical model for the self-inductance of a solenoid. So if I have my solenoid here, if I take the permeability constant, multiply it by the number of turns in the solenoid squared, and multiply that by the cross-sectional area of the loop divided by the length of the loop, that gives me at least a ballpark estimate of how much inductance I get from my solenoid. So what happens when you put a solenoid in a circuit? Well, if you did the lab here, you saw this effect. So here is a diagram of a solenoid wired with a resistor into a DC circuit. And when you close the switch, current starts flowing, but not immediately, because when current starts flowing through that inductor, it induces a back EMF, which fights against the increase in current for a brief period of time before the system settles down into a steady state current that's flowing there. So if we apply Kirchhoff's loop rule to this circuit, if I start here, I increase by the voltage of the battery, and then I decrease by the voltage across the resistor, which is Ohm's law, just the current through the resistor times the resistance. And then minus the voltage drop across this inductor. Well, the voltage drop across this inductor is the same as the EMF across an inductor or a solenoid. So I can write that as the inductance times the change in current with respect to time equals 0. So if I'm at a place where the change in the current is big, I'm going to get a small current flowing through the resistor. But when I get to a place where the change in current is 0, then that's where we get the full amount of current flowing through the resistor and the rest of the circuit. So if you actually graph that current as a function of time, you see that it starts at 0 and goes up with an inverse exponential function until it hits some steady state value, which would be whatever the voltage of the battery is divided by the resistance of the resistor in this LR circuit. So the current through the battery is the maximum current, so that's the voltage of the battery divided by the resistance. Again, times this inverse exponential function, which you may recall from our study of capacitors, is a mathematical function that starts at 0 and then climbs up until it reaches some plateau value. But different from the capacitor circuit, the factors that it depends on are the inductance and the resistance. And instead of being, we saw resistance times capacitance in the capacitor models, here it's inductance divided by resistance. And you could call this the steady state current. Often you see that representation. Again, that's the plateau current that this reaches. And sometimes you'll also see tau written here, again, that time constant. So you have to be a little careful, because in the context of capacitors, we use tau as the resistance times the capacitance. Well, here we're using tau as the inductance divided by the resistance. Both are useful numbers to characterize a circuit, but they're not interchangeable. So this is tau for an RL circuit. It's different than tau for an RC circuit. And if you go on and study more electronics, you actually see what happens when you put all of these elements in a circuit together. So we're going to table inductors for just a bit before we talk about AC circuits in order to talk about what, in my mind at least, is a segue over to the idea of what we mean by an alternating current circuit. So this is a picture grabbed off the internet of a generator, as well as a schematic of what the main functional part of a generator looks like. So a generator is a device that converts mechanical energy into electrical energy. If you've ever used a generator in a storm or anything like that, it actually, you burn gas in an internal combustion engine that produces motion, but that motion in turn produces electrical current coming from your generator. How does that work? Well, briefly, what you have is you have a magnet right here. So I have north and south magnetic poles, so the magnetic field points from one to the other. If I put a conducting loop in that magnetic field, nothing happens in that loop, but if I turn the loop, which is what the mechanical input part is over here, if I turn the loop around, the amount of loop that's exposed to the magnetic field is constantly changing, so the magnetic flux through that is constantly changing, which produces an EMF in the coil and pushes a current through there. And so then if I have some metal slip rings and brushes here, what I'll do is I'll push current out of this system, but because of the geometry of the thing spinning, for half of the time I'm pushing current in one direction and half the time I'm pushing current in the other direction. Now, for your light bulb in your house, that doesn't matter at all. Light bulbs work just fine on this alternating current. And if you were to graph the voltage as a function of time, or the EMF produced as a function of time, you'd see it starts at 0, it climbs up to some peak positive value, back down to 0, then to some peak negative value, back to 0. And so in the context of a light bulb, especially the old incandescent light bulbs, it doesn't matter which direction you send current through it. So it works just fine in an alternating current. And we choose the alternating current in our electrical grid systems to be such that it's switching back and forth rapidly enough that it's not like the light is blinking on and then blinking off all of the time. It heats up and it glows, and by the time it would have cooled off and stopped glowing, it's in the other direction. So you just see steady light out of a light bulb, even though the current is actually switching directions 60 times every second in a US circuit. So that's a brief touch on generators. The other flip of this is an electric motor. So a generator takes mechanical energy and converts it to electrical energy, while a motor takes electrical energy and converts it over to mechanical energy. So if I take my alternating current that I've produced somewhere and I feed it into this system from this end, that will send a current through the coil that's in the middle of the magnetic field. That current in the coil produces a magnetic field, and if the coil in the middle of the magnetic field is not aligned just so, those two fields, the one produced by the coil and the one produced by the permanent magnet, react and cause the coil to spin to try to orient to line the fields up. And if I'm constantly changing the direction and the size of the current through my coil, I can engineer this in a way that this coil turns over and over and over and over again. I've now produced mechanical energy, I've produced motion from this, and I'll get a mechanical output from my electric motor. So motors and generators are in essence inverses of each other. And in fact, you can take, if you've ever played around with small electric motors, they're made to be motors, right, connected to a battery, and it turns a little shaft in the motor. But if you hook it up to some sort of handle and crank it and turn it, you'll actually produce electricity out of the other end. You can use them in both directions. All right. So now that we've said a little bit about alternating current, which is what's produced in a generator kind of system, what happens when we build circuits with this alternating current where we're sending current back and forth periodically rather than always in one direction, which is the DC circuits that we've looked at until now? Well, a couple of things. On a schematic of a circuit diagram, you'll see a little circle with a little waveform in it, that's telling you that this is an alternating current that's happening in this circuit. And so this is a fairly simple circuit where we have an alternating current power source and a capacitor. That's it in here. So we write the function for the EMF that's produced by this power supply using either a cosine or a sine function. In Knight's book, he's chosen a cosine function. And you may recall from your math classes that studying cosine functions, they start out at maximum value, but then they produce this waveform which could be matched to the graph that we saw 2 slides back. So it's a cosine function. It depends on the frequency, and we'll talk a little bit more about frequency momentarily, and it depends also on the time as well. The 2 pi is in here for the mathematics because we need to be able to actually calculate the cosine of some number in order to predict how much voltage we have at a specific time. E naught is then the maximum EMF or the maximum voltage that this power supply produces. So the voltage across the capacitor is going to be also a cosine function, right? When the power supply is pushing current one direction, it's going to be charging one plate of the capacitor up positive and the other plate up negative. But when the power supply switches and flips, then it's sending current the other direction in the circuit. That's going to be discharging the plates for a bit and then charging the opposite plates up. And so the charge that builds up on this capacitor in an AC circuit is not a steady positive plate, a steady negative plate. They are, in fact, switching polarity periodically with the same frequency that the power supply is switching back and forth as well. So we could write the voltage across the capacitor at any time as the maximum voltage that it achieves times, again, a cosine function, the same cosine function that is driving our power supply. Recall that way back we said current was a flow of charge per time, or a change in the amount of charge that's passing some observation point per time. And that capacitance was defined to be the product, or rather the difference of charge to voltage. So I can write charge as the capacitance times the voltage across the capacitor by manipulating the definition of capacitance, and plug that in for charge in my current equation, and see that the current in this circuit that contains a capacitor is equal to the capacitance times the change in the voltage with respect to time. Well, what does that mean? It's helpful to look at some graphs when trying to think about what all of this means. So here at the top is a graph of my voltage as a function of time. So we're assuming it starts out at a maximum voltage, at some point goes to 0, and then it's a maximum voltage but negative. So we've flipped polarity there and we're driving current in the opposite direction in the circuit, back to 0, back to positive, and then that cycle just repeats forever until you turn your power supply off. Well, the amount of time that it takes for the voltage to cycle from the positive to the negative and back to the positive is known as the period, and it's symbolized with a capital T in physics. We'll do more with frequencies and periods in our final unit that's going to envelop a little bit more wave physics before we get into optics. So the frequency is the inverse of the period. So if the period is, 10 seconds, it takes 10 seconds for the voltage to go from positive to negative to positive, then the frequency is 1 over 10, or 1 over 10 cycles per second. So if it takes 10 seconds for one cycle, that means the system achieves 1/10 of a cycle in every second. So they're inverses of each other when we talk about frequency and period. And the voltage across the capacitor can be written as a cosine function, which we mentioned on the previous slide. So maximum voltage is the capitals on these graphs, and then we have the cosine function, and that cosine depends on the frequency. If we increase the frequency, we have more cycles per second, we get more little waves on the graph per period of time. How about the charge? Well, the charge is just the capacitance times the voltage. Again, that comes from rearranging our definition of capacitance. So that means the charge graph is going to look just like the voltage graph is in shape, right? It's going to start out at some maximum charge, on the capacitor. So the capacitor is the most charged when the voltage is the highest. Then the charge actually goes to zero as the voltage of the battery is diminishing. The voltage across the capacitor is diminishing and the charge stored on the capacitor is diminishing. And then we flip, where if we were storing positive on the top plate first, now we're storing positive on the bottom plate. So the charge goes negative for a while, if you will. That's just telling us that the signs have flipped on the two capacitor plates. And then back to zero, and then back to positive. And this repeats it over and over and over again as well. How about current? Current's probably the trickiest one to think about here, but current, again, is the change in the charge with respect to time. And here it's helpful, in my mind at least, to think about the slope of that charge graph. So when the charge is maximum, it's actually not changing very much at all. And so we get no current at that time. But as the charge starts to leak off the capacitor, that slope of that graph gets steeper and steeper and steeper for a while, at least until here. And it's always negative. So there is a negative current that we're getting up until that point. And now the slope is getting less and less and less negative during this part. So that's I guess an increase, or a current that's going back towards being a current of zero. Here's another place where there's no charge change, so there's no current. And this whole current graph can be sketched as the slope of this whole charge graph, or the slope of this whole voltage graph, which is how it's written in here. The current in a capacitor at any time is the capacitance times the change in the voltage with respect to time. So if we start there, we can think a little bit about what's the maximum current that we have here. Well, the maximum current we have here is going to occur when the voltage changes are the biggest and the charge changes are the biggest. And you can show that the changes happen the biggest at values of 2 pi times the frequency times the maximum voltage right here. Now, the details of this, in my mind, are easier if you know some calculus, so I wouldn't worry too much about where this comes from, but just think about the fact that, if you increase the frequency, you're going to increase the peaks that you have for these changes as well. So that means the maximum current, so that's the capital IC here on the graph, is equal to the capacitance times the maximum change in voltage, which we've asserted is 2 pi times the frequency times the maximum voltage across the capacitor. Again, algebraically, doesn't matter what order we write these things in, so I'm going to put all of the stuff that's not voltage in the parentheses and take voltage out of the parentheses, because I'm heading towards Ohm's law here. Ohm's law, recall, says that one way to write it at least is voltage equals current times resistance. Well, if I solve for voltage, I get current divided by this 2 pi frequency times capacitance. And I'm actually just going to define that inverse of 2 pi frequency over capacitance to be a new symbol, which we're going to call X, and it's known as the capacitive reactance. You can think about it in the same way that you think about resistance, but whereas resistance is a steady amount of resistance to the flow in the circuit, capacitive reactance actually is a dynamic resistance to flow in the circuit, and it depends on the frequency at which we're switching the current directions in my AC circuit, as well as how much capacitance that I have here. So if I have a really small frequency, that means I'm not changing current direction very quickly at all. I have a large capacitive reactance. That capacitor blocks current flow in the circuit quite well at low frequencies. But if I crank the frequency up high, so I'm switching current direction back and forth really rapidly, that actually makes the capacitive reactance, the opposition to flow made by the capacitor, fairly low. And I guess the one way I always think about this is if I do this really quickly, I'm not really giving the capacitor time to fully charge and discharge in between my cycles, and it provides less changes to the flow in that part of the circuit. Capacitive reactance also depends on the capacitance. If I have a large capacitor, that actually has little capacitive reactance. But if I put a small capacitor in a circuit, that has the effect of more block to what's going on in that circuit, and there's a larger capacitive reactance. The other piece that we insert in these AC circuits and try to think about what's happening are inductors. So this is basically the same circuit diagram we had for the capacitors. I still have a power supply that has a maximum voltage and a cosine function that's describing how that voltage is changing periodically with time. There's an inductor L in the circuit. There's a potential difference across that inductor that is symbolized with a V sub L. And there's a current that's flowing through that inductor and elsewhere in the circuit as well, which is I sub L. So if the power supply is a cosine function, the voltage across the inductor must be that same cosine function. And so similar to a capacitor, we can write that the voltage at any time across the inductor is equal to the maximum voltage across the inductor times the cosine of 2 pi times the frequency times time. Well, what does this graph look like when we look at voltage and current? Well, again, my voltage graph is my cosine function. So it starts out at a maximum voltage, goes to 0, goes to a maximum negative voltage, back to 0, back to maximum positive, etc. But we actually have this relationship now that the voltage across the inductor is largest when the current change is the largest, and the voltage would be the smallest when the current change is the smallest as well. And so the current changes in the same fashion that the voltage does, but when we start out and we have a large voltage, we actually have a small zero current actually to start. And as that change in current rather decreases, so that even though it's a zero current right here, it is the steepest slope on this graph, so we have the biggest voltage. And then as the current is getting, the change in current is getting less and less and less and less, the voltage across that inductor is dropping to keep this relationship between the voltage and the change in current. So the current through an inductor actually peaks a quarter of the period after the voltage has peaked. So you start out with peak voltage, but that inductor induces that back EMF and fights against that flow of current. And so it takes a while for the current to ramp up, and the current doesn't actually achieve its maximum value until a quarter of the period after the voltage has been the maximum, and which happens to coincide with when the voltage is momentarily zero. So as the graphic points out, this can be described as saying that the current lags the voltage. This, again, is the textbook best case scenario. All inductors, from my understanding, will lag the voltage, but they won't always be by this 1/4 of a cycle. And so for folks that study electronics and characterize circuits, they're always looking at what is the actual lag, and it's often described in context of angles between the inductor and the rest of the circuit that we have here. So if the voltage is the highest when the change in current is the highest, we can write an expression and say that the maximum voltage occurs at the maximum current, which the maximum current is 2 pi times the frequency times peak current here. I'm sorry, this is the maximum change in current, 2 pi times the frequency times the maximum current. And where we're going with this is writing this in similar fashion to what we did for capacitors, which is saying, hey, I can lump algebraically anything I want to together. Let's put everything that's not I in the parentheses here, and let's call that some inductive reactance. Again, playing the role of resistance, but a dynamic resistance that changes depending on the characteristics of the AC circuit that my inductor is in. So when the frequency is high, then the inductive reactance is high as well. If I'm constantly changing the direction of the current in my circuit, I'm always changing the magnetic flux in the middle of that inductor. That's always inducing a back EMF, and in fact, the faster I change the current, the higher the back EMF I induce, so the more resistance to the flow I have there as well. bigger inductor, also more resistance. And so collectively, these are known as inductive reactance. In the workbook, you'll get a little bit of practice with this concept of both inductive capacitant, or rather capacitive reactance and inductive reactance, and how they affect AC circuits.